Okay, this is a problem that looks pretty familiar to types of problems that we've been doing, but there's a few important differences in it, and there's some caveats and some questions at the end that are actually a bit tricky. So I wanted to go over this for a review just of conservation of energy and some basic ideas to show you that the AP problems have some ideas that are very simple and then some ideas that are a bit subtle and a bit tricky. So so you gotta kind of make hay where the sun shines on some of the easier ones for sure, in case you get stuck on some of the tougher ones. So hopefully you've had a chance to try the problem. Let's go through it and take a look. The scoring guide is below too. All right, so you've just got a block coming in. It's going to collide with another block, and it's a frictionless table. So a few of the key ideas, remember, that we've talked about, as long as there's no external impulses on our system's momentum should be conserved. So that should be one of the first things that comes to mind when you see a collision problem, is taking a look at if there's external impulses or not. It's attached to the block 2 is attached to the relaxed spring. Now the spring is nonlinear, so that's something that we haven't dealt with. Usually we've dealt with Hooke's law, and so this is the force of the spring. So we'll be able to deal with that, no problem. I'll remind you about something coming up. So we have a force expression that's not a Hooke-like spring. Okay, and they just give us the block of mass 3m moving to the left. Okay, so the first one is pretty standard. They're just looking for a free body diagram in each mass before the collision takes place, and the spring is not compressed or stretched, so it ends up being a pretty easy question. But the one thing you have to pay attention to is, in a problem like this, you can't just label this Fn and Fg and Fn and Fg. The details are important. Because there's two distinct blocks in the problem, you need to be able to distinguish like one force, normal force, from a different normal force if you were going to set up equations or some different things like that. So you have to pay attention to how you label them. So this would be okay. Let's take a look at the scoring guideline and see what they awarded. So if you take a look at the scoring guideline, what they've got here is same idea, right? Now you can put mg in for the mass, but 2mg and 3mg is fine. But what they want is a point for those, and they want to show that they're not only correct, but they're different from those on the other block. All right, that's what helps earn the point. So details are somewhat important, so I want to show you that. Okay, so let's go to the second part of the question here, part B. So on part B, derive an expression for the speed of the blocks immediately after collision. So remember our big ideas. Big ideas are important sometimes at justifying things. You don't always have to justify if they don't say justify, but you'll have to be able to show them why you think you can use what it is. So remember that just after the collision, that would be before the spring starts compressing, there's no external forces on the blocks. Again, there's no friction on the track or something like that. The only forces are between the blocks themselves, which is internal. So we can use the idea of conservation of momentum. So the sum of the initial momentum of the system equals the sum of the final momentum of the system. All right. So block 2 was at rest. This one's coming in with a momentum of, remember, it's a vector of -3m v sub naught. They're stuck together at the end. The problem states that they stick. So we simply, it's an inelastic collision, right? Perfectly inelastic collision. So we have 2m plus 3m times the final velocity. And so we just do our substituting and come up with an expression for the final velocity in terms of the initial velocity. Now, since notice they ask for the speed, expression for the speed of the blocks immediately after the collision. All right, so since it asks for the speed, we don't have to put the negative sign in. It's 3/5 v sub dot. All right, so how did they award points for this one? If you take a look at the point awarding, basically for you expressing the idea, and you have to do this, show them, right? P1 equals P2, or like I did, the sum of the momentums, right? And express that you're using conservation momentum, you get a point. You should state your equation. Show your substitution of your values. That's where you're getting your next point, right? For showing the substitution and showing the correct answer. So again, write your equation, show your substitution, write your correct answer. Those are always the 3 steps you want to do to earn all your points. All right, let's take a look at step 3 here. Determine expression for the kinetic energy. Well, that one's not too bad, right? So we know that the final kinetic energy is just 1/2 the total mass, and that final speed squared, and we just found that. So we just have 1/2 sum the masses together. This was the final speed that we found, right? 3/5 v sub naught squared. And just do your reductions, and you get 9/10 mv sub naught squared. So you can see this one's lighter point value. They realize that they're just checking to see, do you know kinetic energy, and that's going to be a point. Now let's say you couldn't figure out how to come up with the velocity speed in the first one. You can say in this problem, assuming v sub naught equals something, right? And then put this in the problem and be awarded that point. So if you do get stuck in an earlier part of a problem, continue on. Like so for this one, you might have known how to do it if you knew v sub naught. So state what you believe v sub naught would be. You can substitute that in and keep going. All right, next part of the problem. So this one is a little trickier since we haven't done a nonlinear spring, but it's not that tricky. So whenever you have springs in a problem, right, and you know the initial kinetic energy, they're leading you to the idea that you should use conservation of energy. The problem is we don't know how to find a conservation of energy of a nonlinear spring. It's not going to be 1/2 kx squared. All right, this is 1/2 kx squared came about from kx, integrating kx dx, when we know that it was a linear spring where the Hooke's law is force is k times x, right? If you integrate kx dx, you get 1/2 kx squared. So what we need to do here is take our force function, and if you look at your equation sheet, there's a relationship between, right, work, potential energy. So f of x, like dw equals f of x dx. Remember that potential energy is the negative, right, of the work. So if you have a force function, it's always equal to negative du dx, where u is the potential energy function of x. So what we need to do is we can use this equation from your equation sheet, and this is why I'm showing you this one. This is not one that's often used or maybe remembered by people. So what we want to take a look here is if we use this expression from the equation sheet, we can just see that du is going to be negative f of x dx, right? Just like the work would be f of x dx, the potential is negative f of x dx. So once we have that, we just have to integrate, right? If we integrate du, looks like I forgot to put my little du here, right? From the initial potential energy, which we know is 0 of the spring, to the final potential energy, we're going to go from 0 to d, maximum compression of the spring, negative, right? This negative is this negative. And our force function they gave us was negative bx cubed. So we substitute that in for f of x dx, and we end up with this expression to integrate, bx cubed. All right. So moving from there, pretty easy integral, right? So x to the 4th over 4, evaluated from 0 to d, and we just substitute the d in, and this is the expression we get for the final potential energy. So now we're ready to use our conservation idea, right? Now let's say you forgot or you weren't able to do this. Write an expression for u sub f, try to get some points, and kind of go from there, showing that you know how to use the conservation idea. But this isn't too bad of an idea, and I'm going to end up showing you this in case you end up with something like that with a potential energy. All right, so we just set our initial kinetic energy equal to that final potential energy, and we solve for d. It's definitely a strange expression, so you might not be confident in it, but the fourth root, 18 mv squared over 5b. Okay. All right, so how did they award the points out on that one? This is 4 points of the problem, so take a look here. So understanding that you have to use conservation of energy, you just want to write that idea. They give you a point just for understanding what concept you're going to be using to solve the problem. So write that down. All right, for an attempt to integrate the spring force equation, if you knew that you needed to do it. All right, even if you couldn't remember, most of you probably are going to remember how to integrate a polynomial, but they get a point for even doing the attempt. So you should at least write it down. And then for using the correct limits, so even if you didn't get the integration right, if you had the right limits and you made the attempt from 0 to d, they're going to give you a point for that. So you can get a lot of points even if you don't quite get the integral right. So you just want to have confidence and keep going through these things. And then finally, with the correct answer, consistent with the speed from earlier problem or the kinetic energy part, right, then you can come up with the expression for d, and that's 1 point. So notice all that work that you show is worth 3/4 of the points for this part of the problem. It's only 1 point for getting the right answer for the expression. So make sure you're just doing a good job writing out your work and showing the main ideas, even if you're not confident in the integral or something like that. All right, let's keep moving on. Okay, so for this one, in which direction is the net force, if any, on the block of mass M2 when the spring is at its maximum compression? So the net force is going to be to the right. Okay, once it's stopped moving, obviously the spring is going to be pushing to the right. So one of the things that you could say for your justification, here's kind of the examples that they gave, right? You could show an FBD, that always helps, okay, showing that there's an external spring force acting on the system of blocks. And, you know, you could say the force is directed to the right, and it's going to be accelerated to the right, and so on and so forth. So what you want to do is realize that you just have to write a little paragraph that just simply explains what it is that you're, thinking about there. Okay. This one is a little harder to think about. Okay, it's been a while since we've done FBDs, and so this is why I wanted you to kind of think about this. It says, which of the following correctly describes the magnitude of the net force on each of the two blocks when the spring is at a maximum compression? So think about if you did on the block of mass 2m, right, there's going to be a force from the spring rightwards, and remember that 2m is in contact. Remember, these two blocks are in contact with each other. So there's going to be 2m and there's going to be 3m. So 3m is touching 2m. So the surface of 3m, right, is pushing backward here. So there is a force from block 3 backwards. Okay. Now on block 3m, right, the only thing that's going to be touching it is the force from block 2, right, on block 3. Well, the force of block 3 on 2 and the force of block 2 and 3 are equal and opposite. Okay, so when you realize which one's going to have the greater net force, okay, and in terms of the acceleration, both of them have to have the same acceleration because they're in contact with each other. So A has to be the same. So if you think about that force, right, the force of 2 on 3, okay, or this net force here, right, F net on 3 is going to equal 3m times A. Whereas F net on block 2 is going to be 2m times A. So since their accelerations are the same, since they're in contact with each other, okay, well, what we're going to see is the net force, that probably the easiest way to think about it is just using our equation F equals m times A. All right, and remember this is F net. So when they're asking for the net force, all right, not just thinking about the force between the two blocks, which are equal and opposite, but when you're thinking about the net force on the two, and since they both have to have the same acceleration, the net force on 3 will be 3ma, and the net force on block 2 is going to be 2 times ma. All right, so that's a little trickier one to maybe justify or see if you haven't thought about FBDs for a while and realizing that the objects in contact are going to have the same acceleration. But that's why I wanted to show you that one as well. All right, so this is kind of the explanation, right, that they gave too, and that was worth 2 points. So you can take a look at that. All right. And finally, the last one would be important in some other years, but in this year you don't have to know about simple harmonic motion after the collision. Now, simple harmonic motion only occurs when the restoring force is proportional to the distance that a spring is compressed, and in this case it's not, all right, because it's a nonlinear spring. So this spring mass system would not exhibit simple harmonic motion because it's not a hook spring, right? So anytime you need a restoring force which is proportional to the distance that the object is compressed or stretched, and since in this case it's proportional to x cubed, it would not exhibit simple harmonic motion. All right, but this year you shouldn't have any questions on simple harmonic motion. All right, hopefully that's a quick review and of some things about forces, especially when you have blocks in contact with each other. I think that conceptual part in E here is one of the trickiest things to probably understand, since we haven't thought about that for a while. Whenever you have blocks in contact, just because they're in contact, it doesn't mean that the net force that's accelerating each block is the same. Okay, the force pair is, but not necessarily the net force. So you got to take a look at F net on each block as 3m times A if they ask for the net force. Okay, there could be another question sometime that says, ask, how do the forces between the two blocks compare? Those two forces would have to be equal and opposite, because that's the third law of error. All right, hopefully that helps.